Okay, welcome everyone. Welcome to the 22nd lecture of CS 188. A couple of announcements, actually same ones as last lecture. Your project 4 is due tomorrow at 4 p.m. Your homework 10 actually has been released, I hope, and will be due on Tuesday. And then your midterm, perhaps most important thing to keep in mind, is going to be next week, Thursday. There will be a prep page coming out later today or tomorrow with a practice midterm 2 and also a list of office hours and sections dedicated to midterm 2. Any questions about logistics? Okay, so today's topic is optimization and neural nets. In general, in 188, we try to cover topics that are pretty timeless, such that if 20 years from now, you decide after 20 years of no AI, you get back into AI, that the materials you covered are still relevant. I think we do that pretty well. It happens to be that today, the material we cover also is the fashion of the day. So not only what we think of as a timeless topic, but also the most fashionable topic in AI for the past 5 years, and maybe for another 5 years to go. Who knows how long? So we covered both the most fashionable topic and what we think of as a timeless topic today. So it's a lot more mathematical than most of what we've done in 188. So that was already the case in last lecture. So I'm going to rework through some of the things we covered last lecture to make sure we have the right foundation, and then from there build up to neural networks. So, reminder, what are linear classifiers? Linear classifiers have inputs, which we call feature values, which might come in, let's say, here, 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 and so forth. Each feature has a weight, which is how much attention you pay to that feature. It could be a positive weight or a negative weight. And the weighted sum of the inputs is the activation of the unit. So mathematically, we have a weighted sum happening here. I is indexing over the different input channels. And so we have, let's say, feature 1, 2, 3, and so forth, all indexed by I, weighted sum of those features. And shorthand notation is this dot product notation. Then if the activation is positive, bigger than 0, we might say it's the positive class. If it's smaller than 0, we might say it's the negative class. Pictorially, it might look something like this. So that's a linear classifier. Then last time we said, well, if all we do is this kind of deterministic decision making, it's not always obvious what is the optimal choice of W. It's harder to define if there might not be one that gets everything right. So we transitioned to a probabilistic decision making process where we said, okay, we still have an activation, just like before, that hasn't changed. We call it Z, and it's the inner product of the weight vector with the feature vector that's coming in. If it's very positive, we want the probability of the positive class to go to 1. If it's very negative, we want the probability of the positive class going to 0. So the question is, can we find a function that maps a real number that can be anywhere between negative infinity and positive infinity to the range 0, 1? In fact, there are many such functions that can do this. The one that we picked is sigmoid. What's key about it is that it's monotonically going from 0 to 1. The higher z becomes, the closer to 1. The more negative z becomes, the closer to 0. There were some questions after lecture. Could you use another function there? You definitely can. The key property is this transition from 0 to 1 that's monotonic. One reason people use this one a lot is because when we optimize, we'll need to take derivatives, and this one happens to also have convenient derivatives and is convenient to compute in itself. So there's some practical reasons why you might want to pick this one. But for what we've covered so far, the main reason you pick something like this, it goes from 0 to 1 as you go from negative infinity to positive infinity. So that's the sigmoid. Then the question was, what's the best W when we're going to make probabilistic decisions? Well, we've seen that principle in a previous lecture when covering naive Bayes. It's the parameter vector that maximizes the likelihood of the data. In this case, maximum likelihood estimation comes down to maximizing the conditional probability of the label yi. So we have a data point I, which consists of a label yi and an input xi. And our model will predict the distribution over possible labels, and we want the probability placed on the correct label, the one that's in the data, yi, to be as high as possible. There's a log in front of that. The log does not change things in terms of whether we want it to be high or low. It's just a monotonic transformation. And what this is a sum of log probabilities of all the data points outputs given the inputs. And the score here, the value we achieve, depends on W. Different choices of W will achieve different sums of log probabilities. And what we'd like to find is a W that maximizes this, because that would be the W that best explains the data. Diving into the specifics under that P, the probability of the positive label, given the input xi and some weight W, is this thing over here. It's the linear classifier calculation, the dot product between weight vector and feature vector. And then the sigmoid is applied to that, which is the remainder of that expression, 1 over 1 plus e to the negative activation. And then the probability of the other class is 1 minus probability of the first class when there's only 2 classes. Any questions about this? Because this notation will keep coming back and back and back the entire lecture. Okay, that's 2-class. How about multi-class? So this is 2-class logistic regression. Multi-class, we could say, well, we can now have a weight vector per class. And the weight vector points in the direction that you think the data points for that class inhabit. So then to do multi-class linear classification, you'd say, well, let's look at each weight vector for each possible class I. We can compute a dot product with the feature vector, which describes the input. And then we can see which one maximizes that dot product, and that's the label we assign. But again, that's a deterministic decision rule, and if things are not perfectly linearly classifiable, then it becomes less clear what your right choice is. And so we're again going to define an objective function that characterizes how good a choice of weight vectors is. Okay, so we're going to turn this into probabilities. How do we turn, let's say if we have a 3-class problem, we have 3 activations, Z1, Z2, Z3, into probabilities. This is the equation we're going to be using, which is called a softmax. Let's again interpret this. The first 3 numbers are the original activations, just the results of the inner products. And then these are the softmax activations. Let's imagine Z1 is a lot bigger than Z2, and Z1 is also a lot bigger than Z3. Remember, an exponential looks like this and grows very quickly as you move further on that horizontal axis. So, if Z1 is a lot bigger than Z2 and a lot bigger than Z3, what will happen? E to the Z1 will be way, way, way bigger than E to the Z2, and E to the Z1 will also be a lot bigger than E to the Z3. And what will happen is, in what we have at the bottom here, E to the Z1 will dominate, and we'll have, if it's really a big difference, probability close to 1 on class label 1 and close to 0 on the others. No matter exactly how the Z1, Z2, Z3 are configured, what happens here is they all get turned into a positive number because exponentiating makes it positive. And by dividing by the sum of all 3, we normalize. And so these 3 numbers that we get out will always sum to 1, will always be positive. And the more you're activated, the higher your probability will be in this resulting softmax. Now, what Z1, Z2, Z3 will be for a given data point will depend on our choices of the weight vectors, W for class 1, W for class 2, W for class 3, altogether W. And what we'd like to find is the best W. So again, we can use the same principle of maximum likelihood estimation, which is the principle we say we want to maximize the likelihood of the data that we have over all choices of parameter vector available to us. So in this case, maximizing the likelihood of the data, because we're interested in classification, making a decision, will mean maximizing the likelihood of the labels conditioned on the input. Remember, in naive Bayes, you maximize the likelihood of both x and y together. That's a different optimization. Here, we're just interested in y given x, and we'll try to find w's that are maximally good to optimize this objective over here. Underneath, what's happening? these probabilities are all softmaxes. That is, you had activations, which is weight vector for, let's say, the label class interproducted with the feature vector exponentiated at the top, and then at the bottom, you normalize by looking at all possible class labels, and you look at the inner product of the weight vector for each possible class label with the feature vector, exponentiate, sum it all together to normalize. That's multi-class logistic regression. And that's what we'll be building out most directly in this lecture. Any questions about this? Okay, then what we want to do now in this lecture is find a way to solve for W. The naive way to solve for W is to assume that you have infinite compute, and you try every possible W. And if you do have infinite compute, that is actually a possibility. You can just cycle through every possible W, and then figure out which one maximizes this score. And that would give you the same answer as we're hoping to find with the procedure we're going to describe, but the procedure we'll describe in this lecture will not require infinite compute. So, we've actually seen something similar before. When solving CSPs, we had to find assignments to variables. Think of W as a vector with each entry being a variable, and we're trying to find an assignment to each entry in the vector W. With CSPs, the score would have been how many of the constraints are satisfied. The more constraints satisfied, the better. And we saw something called local search, which was fairly scalable, where we said we start with a random assignment of the variables, and then we just do a random perturbation of a variable, and we see maybe if it's better, more constraints are satisfied, let's keep it. Less constraints satisfied, maybe let's reject it and repeat. So that could be a starting point, and is, philosophically speaking, the starting point for this lecture. You could just pick a random W, and then perturb an entry, see if it's better or worse. If it's better, keep it. If it's worse, go back to what you had before and repeat. That's actually an algorithm you could run, and you might find a pretty decent W if you run it long enough. Some trickiness, though. What we have here is not a discrete domain for the variables. We have continuous domains. So when we pick another value for a variable, there is infinitely many choices. And so we need to maybe be a little more clever about how we're going to pick a reassignment when we have infinitely many choices than when back we did CSPs, and there might have been 3 colors to choose from to color a map. So how do we do this efficiently? One of the things that is actually pretty interesting here is that even though it seems like continuous is our enemy in that it makes it infinite and there is so much more to choose from and to search over, actually it'll help us a lot. Because the beauty about continuity is that you can actually locally get some signal and see in which direction things are getting better and which direction they're getting worse. Whereas with CSPs, you have to make a discrete change. It doesn't give you as much local signal as the way we'll get here. So even though for now it looks like, oh no, continuous is bad, you'll see actually it's a good thing for our optimization process. Okay, let's start with a very simple continuous optimization, one-dimensional. We have a function g of w, and we'd like to find where this function is maximized. If it's really a one-dimensional function, you could just plot it like we did here. That's effectively having the infinite compute. You evaluate the function everywhere, you look at it, and you say, oh wow, this looks good. What's w? This is my w star, the best possible choice. So sure, if your real problem is 1D, just do that and you're good to go. I'm not advocating against doing that, but what we want to do now is we want to build some intuition from the 1D case that we can reuse in the higher dimensional cases. And in the higher dimensional cases, the intuition of just plot it and look at it is just not going to work out. So what else can we do rather than just plotting and looking at it? Let's say we randomly initialize, and this is our W0, random initialization. We can look at the function value, GW. You might say, well, it's good enough. I call it done. My log likelihood has achieved high enough score. But you can also look around and say, what if I change it? Can it become any better? Maybe you can perturb it by a small amount h to the right and to the left. So it would be a W0 plus h over here, achieving this this value here. And maybe a W0 minus h achieving this value over here. You might say, well, moving to the right seems better than moving to the left because the value went up and we're trying to maximize the log likelihood. So then let's step in that direction and maybe repeat this process. Actually, you could probably do this. You could, then again, if you did exactly minus h and plus h, you would end up here, and then you'd choose to go here. Next time you'd end up here, next time here, and then maybe next time, if you're lucky, you land right on the top. And after you do that, you look in both directions. You'll see it doesn't get better. You call it done. You found a local optimum. Doesn't mean you found a global optimum. In this case, we did. But you could imagine if you started, let's say, here, and you did the same procedure, you'd end up somewhere over here. We'll be okay with that in the optimizations that we're doing. We're going to be fine with finding local optimums. We might just randomly initialize a few times and see if we find local optimums that are better or worse with the different initializations, and then keep the best one. So in this case, we initialized twice, once here, once here. We would have found this one, and we'd have retained this one here, and said that's the one that maximizes our score. Okay, so that would mean we kind of discretely perturb a little bit in each direction. You might wonder, how much should we perturb in each direction? And do we really need to do it in both directions? Because if we look in one direction, doesn't that already tell us something about the slope and tell us it's going uphill in that direction, so then it'll be downhill in the other direction if this function is smooth? So maybe we can only look in one direction, or maybe we can actually do something a little different, which is compute a derivative. Compute a derivative, which is this equation over here. What is this doing? It's saying we are at W0, and we're taking the limit of taking a step to the right, to the left, looking at the difference, and dividing by how far we stepped. So this is computing the slope. So it's the linear approximation to the function right here that we're getting. That's what the derivative is doing. You probably covered derivatives a long time ago. Maybe you've seen them again since. The intuition that matters the most for this lecture is that it's computing a linear approximation to your function locally. And it turns out that it typically is not, we'll see more about this later, it's not that hard to compute a derivative. There is rule books for that tell you, if this is your function, this is your derivative. And so you can just kind of use that rule book and say, okay, this is my derivative. Let's say you did this for this function. Then you could say, well, it's sloping up to the right, so I'm going to make a step to the right. And you would make your step to the right. Maybe now you're here. Then here, again, you compute the derivative. You see it's sloping up to the right. You do another step. Now you're here. Compute derivative. Again, it's sloping up to the right. Oops, not here yet. You take another step. Now you're here. It's starting to flatten out a little bit. You'll take another step. And then if you land at the top, you'll see that the derivative is 0. It's a flat fit, which means in no direction can you improve, and you might call it done. So that would be doing a kind of procedure that will generalize to what we're going to do in higher dimensions. At every point, we compute the linear approximation, and we just trust the linear approximation to tell us in which direction to step. We take a step, and then we repeat this process. And notice that this would not be possible if your variables were discrete. If you have discrete variables that take on the values red, green, blue, there's no way to take a derivative against red, green, blue the way you can with continuous variables. So it should start to become clear that the fact that this is a continuous space actually helps a lot in doing this kind of optimization. Any questions about this? Yes? Say it again? So there are different definitions of derivatives. Is the question, does it matter how we define it here? Not really. If you prefer a right derivative or a left derivative or a symmetric like is shown here, doesn't matter too much. Symmetric maybe makes most sense, it's kind of cleanest, but don't worry about those differences. What's key is that the derivative is something that is a local approximation, local linear approximation to your function that tells you in which direction is up, which direction is down. And in fact, also tells you whether things are going up quickly or only gradually or it's flattening out. Okay, how about 2D version of this? And 2D will be the highest dimensions that we're able to draw, but once we have 2D, hopefully the intuition will generalize to higher dimensions in your minds. One thing I want to point out here is when we have a 2D function we're optimizing, often the way we're going to visualize it is by looking at contour maps drawn underneath here. So if you look at those, these are concentric circles shown at the bottom underneath this hill shape. They're showing height contours. On a given line, the value of the function is the same. And in fact, the more you go to the middle, the higher the value of the function, and the more you go to the outside, the lower the value of the function. And often we won't even draw the thing on top. We'll just show those contours, and that should tell you something about where the good parts are. In fact, look at those contours. Somewhere underneath here in the middle should be the right spot, because that's where things get higher, higher, higher. Okay, the procedure we'll use is a generalization of what we just did for one dimensions. Gradient ascent. Now, if you read a bunch of literature and you see gradients appear, often you'll see something appear called, instead of ascent, people will have gradient descent. That's if you want to find the bottom of a function. You descend if you want to find the bottom, you ascend if you want to find the top. We're going to try to find the top, so for us it's gradient ascent. But if you see gradient descent, it's essentially the same kind of idea. It's just applied in reverse to go to the bottom rather than going to the top. In many ways, they're equivalent. It's just a choice whether you're maximizing or minimizing the objective you care about. So, we want to perform an update in the uphill direction for each coordinate, because we have multiple coordinates now. The steeper the slope, so the higher the derivative along a coordinate, the bigger the step we're going to take for that coordinate. That's a choice. That's just the way this is set up. But some intuition as to why this might make sense. If it's very steep uphill in a direction, that's a very promising direction. You might want to put a lot of effort in going in that direction. Whereas in some other direction, things are really, really flat. Well, why would you spend a lot of time in that direction? It seems like there's not much action in that direction. That's the intuition underneath here, but we'll see a little more formal intuition later. So consider a function with two variables, w1, w2. And we'll do updates that are just of the form that we saw on the previous slide, effectively. We'll say, I'm updating my first entry, w1, by whatever it was before. I'm keeping that plus a small change. There will be a learning rate again, like we saw in Q-learning. And this thing here is the derivative with respect to w1. So it's when you are on this landscape here, let's say this is w1, and you're at some point over here, you would say, well, let's see what happens as I move in the w1 direction, which would be effectively along this curve here. If you move in the w1 direction, you move along that curve, you measure the slope along that curve, and that tells you whether you should move to higher w1 or lower w1, depending whether it's an upslope or a downslope aligned with w1, and then you take that step. Same thing for w2. So going back to the picture, we're still here. Let's assume this is w2. We will then consider walking along this curve, but we're not considering the entire curve, of course. We're just looking at the local derivative over here to see what the slope is along the w2 direction. And that will inform us whether we want to increase or decrease w2. And then let's think about this. Let's say the derivatives are all positive, meaning if we move in the positive direction for w1, things go uphill. Then indeed we increase w1. Same for w2. If we move in the positive direction for w1, and that happens to bring us downhill, that means the derivative is negative. Then that negative derivative here will ensure that we move in the negative direction for w1. Let's do this in vector notation. So we have a weight vector w. We update it by some learning rate times this thing over here. This might be new notation to you. What does that mean? It means it is a vector with entries of the vector corresponding to derivatives. In this case, it's a two-dimensional function, so we have a derivative with respect to the first variable and a derivative with respect to the second variable inside this vector. But keep in mind, this thing here is nothing more than a shorthand for saying, I'm going to build a vector with all the partial derivatives. And this thing is called the gradient. So when we say gradient ascent, what it means is we compute the gradient, which is a vector with all the coordinate-wise derivatives, and then we take a step in the direction of that gradient. And based on the reasoning we did here, we know that taking a step in the direction of the gradient moves us uphill. Because if for a certain coordinate the entry is positive, that means we'll move in the positive direction for that coordinate, and that's the right direction. And if for a certain coordinate the entry is negative, it means we'll move in the negative direction for that coordinate, and that's also the right direction for that coordinate. So pictorially, looking from the top, we have some contours here. The highest scoring point is in the middle there. If we run gradient ascent, then we start here. We'll take a step, end up over here, another step, end up over here, 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 and so forth. These steps happen to become smaller. There could be two reasons when you see a picture like this that the steps are becoming smaller. One reason could be that your learning rate was decaying, and so that makes your steps smaller. And that's often going to be the case. Another reason could be things are flattening out. And as things flatten out, well, your derivatives are smaller, and so the steps that you compute based on those derivatives are smaller steps. Now let's ask a question. We've seen the procedure. What is the steepest direction? And I put this at the bottom here just to make sure we keep the notation in mind, which might be new to you. You're hill climbing. You're in the fog. You're on a mountain. And you're saying, well, it's good to measure in each coordinate direction what the derivative is, and then maybe step in that direction or opposite direction based on that. But I'd rather follow the steepest direction uphill rather than doing this per coordinate thing. Can I find the steepest direction? Because that might lead me along the shortest path to get to the top of the hill rather than all these coordinate-wise calculations. Okay, well, we can try to compute that. We're going to be at some point W right now, which is some coordinates that we're at, and we're considering changing our coordinates. And we're only allowed to change our coordinates a little bit. What is this thing here? Delta 1 squared plus delta 2 squared. That is the amount that we move. Remember, if you have, say, delta 1 on this axis, delta 2 on this axis, you have a point over here. This distance over here is square root of delta 1 squared plus delta 2 squared. So how far we move is the sum of the squares, square root of that. So we're limiting how far we're allowed to move. What this is defining is effectively a circular region around where we're currently at. And we're only allowed to move within that circle. And we're going to say, we're asking the question here, which move is going to increase our objective the most as long as we're required to stay within that circle? And if that circle is really, really small, then effectively what we're finding based on that is the direction in which the slope is the steepest. Because if we're going to make only a very small change, and it has to have maximal effect, we got to take the steepest direction. Okay, so also if we're only making a very small change, we can approximate our possibly very complex function with a linear approximation. Assuming it's a smooth function, you can have a linear approximation locally. So our original function g evaluated at w plus delta is equal to g at w plus these two terms, which correspond to the linear approximation locally to the function. And notice that these are derivatives again. It's how much does the function change when I change w1 times delta 1, which is how much we change w1, plus how much does the function change when we change w2 times delta 2, which is how much we are changing w2. We're looking for the delta that has the most effect here, while keeping delta small, because we can't move very far. Notice this guy does not have a delta, so will not affect our calculations. So, actually we want to find the steepest ascent direction, not descent. So we want to maximize over deltas where we stay within a small epsilon circle, this linearized approximation over there. Remember, if we have two vectors, let's say we have a vector A here, and now we have another choice of vector delta, which could be maybe here, or maybe we put delta here, or maybe we put it here. But if delta has to stay within a circle, the way we can make the inner product the highest between delta and A is by making delta completely aligned with A. So we should pick delta pointing this way, and of course can't leave the circle. But this is our optimal choice of delta right there to maximize this inner product. This here is our A1. This is A2, and A transpose delta is A1 delta 1 plus A2 delta 2. So what we see is we have to somehow choose a delta that is of this form factor to maximize the objective. What are these A1 and A2? They're actually the entries in the gradient. In fact, our A is equal to this guy over here. And so what we find is that we should point epsilon, the point delta, in the direction of the gradient, and it can be epsilon long. So the solution will be this over here. It's a normalized vector, the gradient over norm of the gradient. So this thing here is normalized, has norm 1, scaled by epsilon because we cannot move more than epsilon. Which direction it's pointing in? Well, the direction of the gradient. What does that mean? The update we did on the previous slide where we say we move in direction 1 based on the derivative along direction 1 and move in direction 2 based on the derivative along direction 2 is actually giving us the optimal local improvement direction. So even though we were thinking about it with coordinates and we said, well, let's look at this coordinate, let's look at that coordinate, the way we happen to scale the steps along each coordinate, namely we scale them by the derivatives, gives us the direction that's steepest uphill. So we were already doing the right thing to go in the steepest direction. So that's great. We have this optimization problem. We want to find a good W. We can compute a vector of derivatives. That vector of derivatives tells us which direction to step. We step, and we repeat. And over time, we climb the hill till we find, hopefully, some good local optimum. We've seen it in 2 dimensions. In more dimensions, it's essentially the same. The gradient vector will now have more entries. In n dimensions, it'll have n entries. But other than that, procedurally, it's the same. You compute a derivative with respect to W1, respect to W2, all the way till Wn. Those are all derivatives with respect to just one variable. If you know how to take a derivative function with respect to one variable, you know how to do this. You have to just do it many times because there's n variables to do it for. You build your vector, take a step in that direction, and repeat. So this is the procedure. We initialize, maybe randomly, and then we iterate. We compute the gradient at the current position that we're at, W, take a step in that direction, and we keep repeating. And the closer we get to an optimum, then the lower the gradient entries will become because things will start to flatten out, and this will start moving around less and less and less, and hopefully converge. Might wonder about alpha, the learning rate. It is a tweaking parameter. You might have to play with that a little bit to make it work. What would be a rule of thumb when you're like, let's say, optimizing a new function? You're like, okay, what should my alpha really be? Because if you think about it, if you think of your function g of w, and somebody else gives you a new function that is 10 to the 6th times g of w, you're solving the same problem in many ways. But if the function is 10 to the 6th times g of w, your gradients will all be scaled up by a 10 to the 6th, and your steps will be 1,000,000 times bigger, even though you're effectively trying to solve the same problem. So you can't just have a general learning rate that will work all the time, because somebody could come in and just rescale your function. That learning rate will not work anymore for you. So how do you get this to work out? Is by looking into the W space. So you might say, let's compute a gradient, update. Let's see, okay, how do I rescale this gradient vector such that my update to W changes W about 0.1 to 1%. If it does that, then it's reasonably sized, and I'll repeat this, and over time get to a good point. If you do this to decide on your alpha, somebody can rescale your function by 1 billion, 1 trillion, and it will not affect what you do with your W. It'll all be the same update, because you'll measure the size of your update based on what happens in W space, not in however somebody might have rescaled your function. Okay, so now we know how to optimize. Now, in fact, we've covered something much more general than maximizing likelihoods. We've covered the notion that if you have a function, g, that depends on some variables that are continuous variables, how can you start from a random point and from there improve to land at a better point for that score that you have? Let's go back to learning. We want to maximize the log likelihood of the data, in this case, labels given the inputs. Okay, same thing. We can write out the gradient ascent procedure. Our G is now the sum over all data points of the log probability of label given input under the current W. Other than that, nothing has changed. Now, the gradient of a sum is the sum of the gradients. So actually, that's rewritten this way over here. That's our general procedure. Now, if we look at this, you might say, well, it looks like we do a bunch of updates summed together to update W. So I have to go through all my data and compute these gradients, and then I do an update. But what if I just computed one gradient on one data point? Wouldn't I already have some information that I can use to improve W right away, and only then go look at the next data point, then go look at the next one? So I don't have to, let's say if I have 1 million data points, do 1 million calculations of gradients before I can do a change to W. In fact, you'd be right. You can do that. That would be called stochastic gradient descent. What you do there, once you've computed a gradient, you right away incorporate it. And the upside here is that when you compute the next gradient, you're computing it at a better point on expectation than where you would have computed it otherwise. So you don't waste your time computing 1 million gradients at the same point. Those last gradients are already computed at a way, way better point than you started from. So what does that look like? You still have a kind of infinite loop here till you decide you're happy. You pick now a random data point and just compute the gradient for that data point of the conditional log probability of label given input. Do an update, you repeat. Now you might say, well, that means I compute this gradient and I'm waiting there before I can compute my next gradient, but maybe you're computing on a computer that has a lot of parallel compute power. Maybe your GPU can feed through many things in one go in which you do effectively the same calculation. Then you'd be waiting and not utilizing that. So actually what people mostly use in practice is something in between the two versions we just saw. We first saw batch gradient descent, which is look at all your data, sum the gradient together, take a step. Then we looked at stochastic gradient descent, where we look at one sample, do an update, another sample, do an update. And in some sense that's optimal, except that if you have parallel compute, you're not utilizing it. If you do have parallel compute, you'd say, well, let's take a batch of things. So instead of taking one, I take a batch of examples. Let's call that batch J. And then I sum together the gradients for each data point in that batch, which I can do all in parallel, those gradients. And then I just reduce, sum it all together, and do an update based on that. So that way, if you think about wall clock time, you're not wasting wall clock time waiting for one to be done and then be able to do the next one. You can keep running and utilize your GPU kind of to maximum cycles it provides to you. And so typically, if you ask how big should this batch be, typically this batch will be determined by how much you can compute in parallel. If you can feed 100 examples in parallel, you might feed 100 through. If you can compute gradients on 1,000 in parallel, you'll feed 1,000 through. If you can feed 1 million in parallel, sure, 1 million go through. That will, whatever you can feed through in parallel, is what you would feed through to optimize your wall clock time when you do this. And this one is called mini-batch gradient descent, where mini-batch refers to the fact that batch means everything, your entire training data. Mini-batch means that you take still a batch, but smaller than your entire batch of training data on which you do the gradient calculations to get your update. Any questions about this? How about computing all the derivatives? Because we've been assuming that we can just say, hey, give me a gradient, and then we just take a step in that direction. We'll look at that later. So let's not worry about that for now. I'll revisit that at the end of lecture. So once we've seen also neural networks, which are a generalization of logistic regression, and will beg the same question. Okay, let's take a 2-minute break here, and then let's generalize this all to neural networks. All right. Any questions about the first half? Yes. So the question is, can we use linear programming to solve this kind of problem? It's an interesting question. So we think about what is linear programming? Linear programming is a methodology to, well, you can think of it as a methodology or a problem formulation. So linear programs are optimization objectives like we saw here, but where the objective has to be linear. So the function itself you're optimizing is linear. Now the reason it still is interesting, because if it's just linear, you just run to infinity, and that's where the highest number is that there are also constraints. You have to stay in a certain region. And the boundaries of that region are also linearly defined. And so linear programs are optimization problems like this with an objective, but also have constraints. And the format that is available to you is very limited. Objective has to be linear, and the constraints have to be linear. If your objective is of that form, and possibly you have constraints, then definitely you can use linear programming, no problem. But for many, many problems, the objective will not be linear. And if you have constraints, which we don't have here, but if you had constraints, they might not be linear, which might limit how much you can use the kind of off-the-shelf linear programming toolboxes. But if their assumptions apply, they're highly optimized to do a great job at solving those problems. If you look at what's underneath, some of them use very specialized ideas like simplex. Others use gradient-based methods underneath too. And then it would come back to something very similar to this. Yeah, so interior point methods are ones that turn your linear program with constraints into an optimization problem where there's no constraints anymore, but the objective is changed from linear into something that rises to infinity at the boundaries, and then you're back, and you're minimizing in that case, and you're back to a similar setting we have here where a gradient method can find the optimal solution. And so it would end up being extremely similar to what we cover here. You'd have to do first a transformation step, turn some constraints into objective terms, and then you'd be in a very similar situation. Any other questions about what we saw so far? Because we're going to strictly generalize this now. Okay, neural nets. We've kind of already seen a neural network, namely the multi-class logistic regression, re-shown here, drawn out more explicitly as a network, is an example of a neural network. We have inputs, feature 1, feature 2, feature 3, up to feature k. They then get somehow fed into this network thing that computes activations, Z1, Z2, Z3. Remember, what was Z1? Z1 is just some weight vector for class 1 interproducted with f of x. And so what does this drawing mean? Well, weight vector 1, first entry lives here. Weight vector 1, second entry lives here. Weight vector 1, third entry lives here. Weight vector 1, kth entry lives here. Those weight vectors are used to weight the input features, compute a weighted sum, get your Z1. Something similar is true for how Z2 is attained and Z3. These activations can be between anywhere negative infinity, positive infinity. You want to turn it into probabilities. That's where the softmax comes in. And we get out conditional probabilities for each possible class given the input. Now, we still have some work to do here in practice. I mean, we now know how to optimize, but when you apply this in practice, you'd have to think about what should be good features. Should I count the number of loops that I detect in my image to do a digit classification? Or should I count the number of edges that are vertical in this part of the image? Should I have as a feature whether this pixel is dark or not, and so forth? So those are choices you make, and those define your feature vector. You might wonder, can we maybe more automatically figure that part out too? And that's where bigger, deeper neural networks come into play. So instead of just having this, what we just have here, we're going to make it a lot bigger. We're going to make it a deep neural network, and we're going to learn the features. So we have our original, what happened? We have our original inputs over here, let's say pixel values. And we want to turn that into interesting features on which we can do a multi-class logistic regression calculation to classify what's in the image. What needs to happen there? Traditionally, what would happen is you would think very hard about what you think matters, then write a piece of code that turns your x's into f of x's. But ultimately, that piece of code, that's all it is. It's some code. It's some calculation. The main idea in deep neural networks is to say, stop counting on people coming up with that calculation. Just let it figure it out on its own. Let's put a massive amount of calculation there that looks a lot like what we already saw. And that massive amount of calculation, we're not going to program by hand what's happening there. We're going to leave it flexible. And hopefully, it results in good features that can then be used in the multi-class logistic regression to find a good classifier. And so the massive amount of computation is what lives over here. it turns the input values x into feature values f of x. What's actually happening here, each circle corresponds to effectively a neuron, loosely inspired by neurons, so it's a network of neurons, and each one of them does a calculation that looks like this. So it's saying, I'm taking a weighted sum, so a sum that's weighted, of my inputs. To compute an activation of a neuron in layer K, we use the neurons in layer K minus 1 and take a weighted sum of the activations in layer K minus 1. You might wonder, is this a good choice? Is this really what we want? If we want to compute features, do we really want kind of just like a bunch of neurons that take weighted sums of what's in the previous layer and pass that on and repeat? If you just take weighted sums, pass on and repeat, it's actually not going to work very well. That's why there's still this little g up front here. G looks at what comes out of the original calculation, which could be anywhere between negative infinity and positive infinity, and then rescales it in some nonlinear way. Why? If everything is linear, if you don't have G and everything is just linear, everything stays linear. And you get nothing new by having many, many layers. Because linear times linear times linear times linear, however many times linear, still linear. But linear followed by this G thing is nonlinear. And then you do linear again, followed by G, is more nonlinear, more nonlinear, more nonlinear, more and more flexibility in what you calculate. And we'll see something later that if this thing is big enough, and indeed you have a G in there, you will get a very expressive program living there. And that's the best way to think of it. This is your feature calculation program. If you prefer to calculate the features by a program you write, by writing lines of code, that's fine. That's the traditional approach. The more popular approach these days is that you don't write lines of code for that feature calculation program. You just give it a massive network. And how does it get programmed? Well, you find the W's, the weightings on all the connections that result in good features, such that you do get a good classifier on your data. To unify notation a little bit, instead of calling these F1 through Fk, and note that the number of, actually, two things. First, we'll unify notation. These are all Z's early on, and that's F. They're the features, but just to unify, we'll call those Z for the nth layer. So the nth layer in the neural network happens to be the features that go into the multi-class logistic regression. Then, when you look at the bottom here, we have capital L input numbers. Then we have, or pixel values, whatever it is, we have layer 1 has capital K1 number of hidden units Z. Layer 2 has capital K2. Layer n-1 is capital K n-1. And then layer n has capital Kn. So it could be that you have 10 inputs, then the next layer has maybe 100 Z's, the next layer might have 1,000, then 1,000,000, then maybe again 10,000, 1,000, down to 500, and then maybe at the end you're down to 3 that are over here, that are your output activations, which get turned into a probability through the softmax. So even though the drawing here is very symmetric, keep that in mind. It doesn't have to be the same number in each column of hidden units. In fact, it can vary very wildly. Might wonder about this G. What might it look like? The popular choices in practice look like the blue curves shown over here. These figures also have a yellow curve. The yellow curve is the derivative of the blue curve. Don't worry about it too much, but you can imagine, given we're going to have to compute derivatives, it matters that these functions have derivatives that we know about, because we're going to need derivatives. But look at the blue one, sigmoid. We've looked at that one a lot before. That's how to squash something between 0 and 1. Negative infinity goes to 0, positive infinity goes to 1, and gradual transition in between. How about hyperbolic tangent? It actually looks very similar. Look at those two. look at it very carefully. You'll see they actually kind of look the same, except that one of them is kind of just shifted a little bit and expanded. This one here, hyperbolic tangent, goes from -1 to +1 instead of 0 to 1, but otherwise has the same shape as the sigmoid. You might wonder why might people care about having both of those. If you have one of them, isn't that enough? Like if they're the same shape? Sometimes when you think about your problem, it makes more sense to think about things as being on versus off. And that's where the 0, 1 can make a lot of sense, because you multiply in a 0, that's kind of an off thing. Nothing comes through. Sometimes it makes more sense to think of it as negative versus positive activation, and then the hyperbolic tangent can make more sense. There's also some practical reasons why often the hyperbolic tangent works a little better, is because your numbers tend to be centered around 0, which tends, for a lot of optimizers, when you do a gradient descent, it tends to work a little better when things are naturally centered around 0 than when they're offset away from 0, which you have in the sigmoid. So your default choice might more likely be this one here than the one on the left, but both can have their merits. You might wonder, if we have to compute derivatives, a lot of work, what's the simplest thing we can do to make sure things are not linear, but as simple as possible? That's the rectifier. Rectified linear unit, the function runs here. If you're lower than 0, you stay 0, or you become 0, and if you're higher than 0, you stay what you are. So this is very similar to linear. Any positive thing is essentially just passed through as is, and a negative thing becomes zeroed out. So that's also very fast. You don't have to compute any exponentials to compute this thing. You just check, bigger than 0 or not, and set to 0 as needed. So it can be computed very fast. Derivatives are very easy to compute. No exponentials involved either. I mean, this thing contributes either a multiplication with 0 or a multiplication with 1 to your derivative calculation. So very, very simple. It is probably the most popular one right now for people to use. But all three of these are reasonable. What's key about them is that none of them is just a line. If it's just a line, it's not going to work, because that is linear, and if things are linear and linear and linear and linear, you don't get enough flexibility to capture nonlinear patterns in your data. Okay, so training the weights. Question, yes? Sure. That's pretty much it. I don't think it's exactly the same thing, but it would get pretty close. It might even be the same. We'd have to do some calculation. But there is, it's roughly something like that. You scale it by a factor 2 and shift it. So it might be right that times 2 minus 1 does it, or it might be something very close to that. So, to find W, which is now not just the W for the multi-class logistic regression, but the W's that live in the entire network, we can just have the same objective again. We've already seen this pattern many times now. We just try to maximize the probability of the labels in our data given the inputs for the corresponding data points. Different choices of W will lead to different scores. We want to find a W that maximizes this score. This again is a continuous optimization, because the W's live in continuous space. So we can follow the same procedure. The W will be a lot larger vector, so computing a derivative with respect to every entry of W will take a little more time than when you have a smaller W, but it's the same principle. You just run gradient descent, and you stop when the log likelihood of your holdout data starts to go down. Right? That's always what we do in this kind of training. We train on our training data. That's what gives us our gradients, but we've got to be careful we're not memorizing our training data. We've got to learn the pattern in the training data that generalizes to other data. So once on the other data, the holdout data, things start going down, we call it done. That's our result. What are some properties? Here's a very interesting property, and this is part of why neural nets are, in some sense, pretty well justified and so popular, is the universal function approximation theorem. That says that even just a 2-layer network, if you just have one layer of z's added on to what we used to have, if that layer is big enough, that network can approximate any mapping that's continuous from input to output to arbitrary precision. So no matter what function you're trying to learn from your input to output of your data, if your network is big enough, you'll be able to learn that pattern. Now again, do keep in mind, you don't just want to memorize that pattern, of course. You want to stop the training once the holdout accuracy starts going down, but the network, in principle, can learn the entire pattern in your training data if your network is big enough. Okay. What's happening underneath? Effectively, you're learning the features. You're turning your original raw pixel values or your word counts or whatever it is into something more meaningful to do a classification on. More formally, and the star here means that you're not expected to understand even the phrasings of these theorems, let alone the proofs. But there is a bunch of formal theorems saying that if your network is big enough, it can capture up to arbitrary precision any mapping from input to output that's continuous. And there's a bunch of papers that came out around the same time, late 80s, early 90s, stating this. If you've taken a signal processing class, you might actually have seen something similar. If you saw Fourier analysis, they would say, okay, if you have a function that's periodic, you can approximate it to arbitrary accuracy with a sum of sinusoids. Well, the same thing is happening here. We're saying if you have a function that's smooth, nothing about periodic here, but you have a function that's smooth, if you have a big enough network, that network can approximate that function to arbitrary precision. Okay, so that's a good thing, because that means that if somehow our network is not capturing the pattern, we know what to do. You can say, let's just make the network bigger. Now again, you might end up overfitting. You ought to be careful there. But if your network does not capture the pattern of what's in your data, and the accuracy doesn't really go up anywhere, you might just want to make your network bigger. Let's play around with this. So here's a demo site where we can look at some examples. So here's let's choose a linearly separable data set here. Okay? 2 classes, linearly separable. Now, it's not finding, the initialization does not have the right classifier. We have 2 inputs, x1 and x2, and this is the output of the classifier. Let's train it. So we take a step. Wow, after 1 step, it's already gotten pretty far, and it's aligning itself a little more to make those probabilities higher for those data points. And let's run this faster. You see it's making those probabilities even higher. It's going to make that sigmoid steeper. And it got everything right. Okay, now let's take a look at if we add some noise in our data. So let's put a bunch of noise. Okay, so now there is no linear separation for data points. We can again run logistic regression, which is what's happening underneath. Do update. The mini batch size here is 10, so at every update is taking the gradient according to 10 data points, doing an update, repeat. As we keep going, it starts aligning this thing. It's not going to find a solution that's perfectly precise on the training data, but it is finding a solution that, you might argue, captures the correct pattern from that training data. Now, let's reduce noise again, all the way to 0. Let's take a more difficult data set, this one here. What if you run logistic regression now? Well, let's run it, see what happens. Doesn't do too well. You see, nothing is very dark blue, nothing is very dark yellow, meaning nowhere it's very confident about the labels. The labels are never confident, and rightfully so, because it's often wrong about the labels, so it's putting the probabilities closer to 0.5 for most of them. And that's the best it can do here. Okay, but we've seen if we have a neural network, we might be able to do something more expressive. Let's add some layers. Okay, let's add a hidden layer. How many units do you want here? Well, let's start with 2 units. Let's train and see what happens. Okay, it finds something where for 2 of the regions it does pretty well, and then the other region it assigns kind of like a 0.5 probability, it doesn't know. Well, you've seen the universal function approximation theorem. It says if your network is big enough, it should be able to capture the pattern in the data. Well, if you're not happy with this, let's make the network bigger. Let's add more units. Actually, let's keep the same number of layers for now, but add more neurons in this particular one layer we have. Actually, think about it. How many neurons do you think you need to capture the pattern in this data? 4. Why? Well, intuitively, 4 makes a lot of sense, right? Think about there's, in some sense, 4 regions. So you kind of want to be able to point in all those 4 directions. That's what your first layer could do. And then the next layer could say, well, if one of these 2 is active, it's blue. If one of these 2 is active, it's yellow. So the first region splits into 4, and then the next one consolidates. So let's see what happens when we have 4. Let's run the training. And we see that's indeed starting to capture the pattern in the data pretty well. What's this blue one doing at the top here? Not clear. That's probably overfitting. There's nothing blue there. There's also nothing yellow there. That's kind of thing where probably we've overtrained at this point that it popped up with something blue over there. What happens if we make the network even bigger? We add more neurons. More neurons. Let's train again. So far, the nonlinearity we've been using is tan h. Okay, that was one of the choices. What if we change this into linear? Okay, we've got a big network. Everything's linear. The G function is doing nothing, just identity. What will happen when we train? Let's see. Your prediction, hopefully, was it's not going to find a good solution. Because if everything is linear, it's like having a linear classifier that has only just one layer, no hidden units, and that's the best you can do, and it assigns roughly 0.5 probability in most places here. How about another nonlinearity? ReLU, which was the thing that below 0, you become 0, above 0, you stay what you are. The minimal thing to become nonlinear is like have essentially 2 lines, right? Let's see what happens. ReLU, no problem, finds a nice solution here. How about another data set? This one here, concentric circle. Let's remove some hidden layers. Let's think about what will happen when we just try to learn a linear classifier. It's not going to do too well, right? No matter how long we train, and I'll probably make sure that it's not too confident anywhere because that would give it a very bad log likelihood score. If you're confident about the wrong thing, that gives you a bad score, so you want to be somewhat unconfident in most places to make sure you don't make bad mistakes. What if we add hidden layers? Let's see. Let's add one hidden layer. We have ReLUs. Let's train. And it's able to parcel out that middle region. If it hadn't been able to do it, then we could have just grown the network more. What if we only have one unit here? What will happen if you just had one unit in your hidden layer? That doesn't allow you to do much, because that one unit effectively is like one classifier, one linear classifier. You're saying, I'm going to first run one linear classifier on my data, and all I get to do later is then use the result of that one linear classifier. So if I do something like that, hold on. If I do something like that, training, it's not going to do very well. It's not going to help much to have that one hidden layer, because it's not giving you additional expressiveness. It's essentially still just a classifier. You need a lot more to be able to get the expressiveness to fit to this kind of data. Not a lot more, in this case, just 3 more. How about something even more complicated, this spiral? Can we fit that? Well, let's see. With 4 hidden units, can we do it? It's trying. It's trying. It's getting some of the points, but not that many. Well, let's just make the network bigger. Let's add some neurons here. Let's add some more layers. Let's make those layers big enough, because this is a pretty complicated pattern to capture. And let's see what happens. Train this thing. It's not easy, right? that this is a complicated function to fit, so you see it takes a long time for it to make progress. It's hard to figure out how to move W, and it's very subtle what you have to do to make progress on this, but it is making some progress. If you look at the learning curve over here going down is good because they count the number of errors rather than the accuracy. You see that over time, it's really starting to capture the pattern. There's still some weird overfitting happening, for sure, if you look at this, like the blue ray that kept shooting out of here. But at this point, it's actually pretty much there. So even though it is a very complicated nonlinear pattern, having a network where each unit has its own local nonlinearity is enough to be able to capture this. So this is publicly available, this demo. It's linked from the slides. It's a lot of fun to play around with to get intuition for what kind of neural network capture or not capture in terms of data patterns. Okay, so how about computing all the derivatives that we need? Well, you probably all have taken classes at some point that resulted in a table like this. This table effectively tells you, for every function that's in that table, what's the derivative. We might say, well, nowhere in that table do I see my neural network. It's just not in there. Will there be a book that has your neural network in that table? Probably not. Usually these tables have sines, cosines, and x squared and x to the third and so forth. They don't have this massive neural network in there and then saying, here's the derivative. What these books do have, though, is something called chain rule. Chain rule says if you have a function that consists of the composition of multiple functions, you can compute the derivative of that composed function by computing derivatives of the components and multiply them together. And that's what a neural network is. You have a sequence of functions being composed together to go all the way from the input to the output, and you just apply the chain rule many, many times. If the network is big, you'll have to apply the chain rule of, let's say, 100 layers deep. You have to apply the chain rule 100 times because you're composing 100 times. But that's all you need to do. So there's rules for this. Doesn't mean it's painless to work through this. Like if we give you a network and we say, give us the derivative with respect to weight 3 in layer 2 of this network, given this data, that would be a lot of work for you to write out by hand. But the rules are very well defined. So actually there's no reason to be doing this by hand. These rules are very well defined. Any composed function that ultimately reduces to the things that are in the table here, you can just apply the rules and call it done. It'll automatically generate a solution. You go to Mathematica, something like that, you input a function, outputs often a massive derivative thing of that function. So there's something called automatic differentiation, which does that for you. It'll say, okay, you give me a function, I will look up in those tables and I'll apply the chain rule for you, and here is the result for you. That's what these tools do. Some tools or brand names of the tools are Theano out of University of Montreal, TensorFlow out of Google, PyTorch out of Facebook, Chainer out of Preferred Networks. So these are alternative tools that there are, of course, subtle differences, but at a high level do the same thing. You can feed in a function, and out will come the derivative of that function with respect to whichever variable that you want the derivative with respect to. In fact, if you have a function, in our case of the form g, x, y, w, x the input, y the output, and w all the weights, you can ask for the entire gradient vector in one go, and there's an efficient way to reuse calculations you do for the different entries, such that actually you can compute the entire gradient vector at the computational cost of roughly 2 to 3 times the cost of just a forward calculation through the function. So you might have thought derivatives are expensive, we're going to have to wait a long time to get those out. No, if you can do the forward calculation through the network, there's a backward calculation that only takes 2 or 3 times longer that will give you the entire gradient vector. Okay? For this class, you just need to know that this exists, that this is the case. You don't need to know the details of how it's done. I mean, if you want to go look it up, there's a lot of tutorials online telling you about what is backpropagation, what is automatic differentiation, and so forth. We're not going to quiz you on that. We're not going to expect that you know that, but know it's possible. Where you can do a forward calculation at just 2 or 3 times the cost, you can do a backward one. Okay, summary of the key ideas that we've covered at this point. The way we've formulated learning classifiers is by optimizing the probability of labels given the input. Optimize the probability of all the labels. The product of the probabilities of the labels is the same as it's equivalent to optimizing the log of the product of the probabilities, which is the sum of the logs, and that's what we've been doing. So we maximize the sum of the log probabilities of all the labels given the inputs. Against what? Against W, which is all the weightings that we have in our network. W is a continuous vector. It turns out that helps us. We can do gradient descent. We can locally look at the derivative of our objective with respect to each of the entries in W and use that to choose a direction in which to step. And that direction, the gradient direction, is the steepest increase in our objective direction. So it's the fastest way to increase our objective with a local step. We keep doing this till we hit early stopping, meaning we hit a point where on the holdout data, accuracy starts dropping, because that means we're memorizing rather than learning the pattern. What does it mean to have a deep neural net? It means that your last layer would still be a logistic regression in what we covered, but now there's many, many more layers coming before that. And those replace, in some sense, human ingenuity of deciding what is a feature. Do you do a word count, a log of a word count? Do you do loop counting? Do you do connected components counting? All that stuff gets replaced by, here is a massive neural net, and we know it can approximate any function from input to output. Well, let it find the one that is the right features from looking at the data. That's what the universal function approximation theorem tells us. Network large enough, then neural net can approximate any continuous mapping, including the one that we want, and hopefully this gradient descent procedure will find that one. Sometimes we need multiple initializations, multiple runs, but often it'll find a very good one. This gradient itself, well, that's just a vector of derivatives. A vector of derivatives, principle, nothing special about that. You just take derivative with respect to each of the entries, each of the weight vector entries. In practice, could be a lot of tedious work to do that if you're going to do it by hand, but luckily there are automatic differentiation tools which allow you to just input the forward calculation, specify the network, and then it'll do the backward calculation that gives you the derivatives. How is that done? That's outside of the scope of 188. How well does it work? Let's see, we got 3 minutes left, which is not enough to really cover how well this works. So let's shift those slides to Tuesday. All right, that's it for today. See you on Tuesday.